What's going on, guys? Savor Sauce here, back with another video. So today we're going to be doing something a little different. Usually my tutorials go on for kind of a long time, but today I'm limiting myself to 15 minutes. So if you're in for speedy tutorials, make sure to like and subscribe. So before I start, just so you know what we're doing, we're making a image classification model using PyTorch and then training it, and I'll walk you through how everything works in 15 minutes or less. So let me just pull up my timer. Let's 15 and start. Okay, so first thing we're gonna do is import dependencies. So I'm just gonna comment import dependencies. So just make sure to install all of these before you start. So we're going to import Torch, import CV2. Actually, no, we're not going to use it, CV2. That would be if we're working with images, which we are, but we're not going to need it. So import torch.neuralnet as neuralnet. Import torch.optim as optim. That's for our optimizer. From torch.utils.data, we're going to import data loader to load our data, and then data set. From torch vision, we're going to import data sets and transforms. We're going to import torch vision. We're going to import, so from torch info, we're going to import summary. TensorFlow has a summary feature, but PyTorch doesn't, so this external module is going to allow us to make our summaries. And then we're going to import matplotlib as or .pyplot as plt, and then we're going to import numpy. Actually, no, we're not going to need numpy, it's fine. Alright, so now we're going to run this. So this next, while that's running, this next line of code may not be important if you don't have a GPU, but if you do, you're going to want to include this. So we're going to set our device equal to CUDA if torch.CUDA is available. Else, we're just going to use CPU. And I'm going to print out the device here so you can see. So mine says CUDA. If yours doesn't say that, and you have a GPU, go check out a video I made a while back about installing CUDA for PyTorch. So now we're going to get into our code for the model. So I'm going to comment out model instantiation. So class, we're going to call this simple CNN, and it inherits from nn.module. So we're going to define our init, which takes in self, and then number of classes, which has a default value of 10. So we're going to get all of our stuff from the module we inherited, like this. And now we're going to define our model architecture. So I'm just going to call this self.architecture. Did I spell that right? Yeah, I think so. It's going to be equal to neuralnet.sequential, and then we're opening parentheses. So the first layer is going to be a conv2d, and it's going to go from 3 to 16. So the 3 is for all the RGB channels, and then our kernel size is going to be equal to 3. The stride will be equal to 1, padding also equal to 1. Then we're going to give it a ReLU activation, and then we're going to give it max pool. We're going to pool the filters, so we're going to make them smaller is what that means. The kernel size equal to 2. It's also stride is also equal to 2. Then we're going to include a layer of batch norm, which takes in 16. Then we're gonna add in another conv 2D layer, which is gonna take it from 16 to 32. Also, kernel size equal to 3 again. Stride is gonna be equal to, we'll put stride equal to 1 again, and then padding will also be equal to 1. And then another ReLU activation function. This needs to be capitalized. Make sure you have all of your capitalizations correct. And then we're gonna include another max pool layer. Like that. Same kernel size as 2 and stride as 2 it's the same as the last layer. And then another layer of batch normalization. And this one is going to have 32 inputs since we have 32 filters at this point. Then we're going to go up again from, we're going to do another conv 2D layer, and we're going from 32 to 64. Same kernel size, it'll be 3. Kernel size equal to 3. Oh my god. And then stride will be equal to 1 again, padding also equal to 1. Another ReLU activation. Another max pool. And we're taking in 64 this time. 64. And then we keep the same kernel size. And then also the same stride. And then after that, we're going to include another layer of batch normalization. Takes in 64 this time. Now we're gonna use a flatten layer, like that. And we're gonna flatten indices 1 to 3, or dimensions 1 through 3. So the last 3 dimensions. Then we're gonna feed that into a linear. This is the same as a dense layer if you're used to TensorFlow. So this is going to be equal to 64 because that's the number of filters we have at this point, and they're each 4 by 4 pixels. And then we're going to bring that down to 512. Then we're going to include another ReLU like that. Then we're going to use another linear. That'll go from 512 to the number of classes that we have, which in this case is going to be 10. And then that'll have a softmax activation, where the dimension should be 1. Alright, so that's our model. And then we're going to define our forward, which fortunately, since we're using sequential, is very easy to define. So we just do that. And this should take self and x. X is going to be equal to the, we're going to input that into x, and then we're going to return x like that. Okay, so that's our model done, but now we want to see what our model looks like. So we're going to just instantiate some values. So the batch size for this training is going to be 16. Or no, actually, let's do 64. If you have memory constraints, you can lower the batch size all the way down to 1 if you need to. And that'll make the training, it'll take longer. But it'll be quicker, and you'll be using less memory at the same time. So then we're going to change the learning rate. It's going to be 0.001. The number of epochs, we'll do 20. The input shape is, I think, 64, 3, and then, or for this, let's just put batch size in case you guys change your batch size. And then it'll be 3 by 32 by 32, I think. I'm not quite sure. But it should be, it doesn't really matter, it has to be close enough. And then our model be like that. And then we're gonna do our summary. So model and then the input shape, input size is equal to input shape. So let's run that. Oh, hold on. Be like that. Let's see. Kernel size. So this line is giving us an error. Let's see. Why are we getting an error? Kernel size. Interesting. Well, this... Oh, I see. We don't need to input the filters here. So now I'll run this. Right. So now we should take that. We're not doing that. It should be like that. There we go. So we have 500 or 553,000 parameters. That's reasonable. Alright, so now we're going to do our transform. It's going to be equal to transforms dot compose. So we're gonna first convert our images to PyTorch tensors, and then we're gonna normalize them. So the mean is gonna be 0.5, 0.5, like that, and then the standard deviation will be the same, like that, and then that's that. Just load that. Okay, so now the train data set is going to be equal to data sets var 10, oh, like that. So the root is going to be equal to data. Train is equal to true on this one. Download is equal to true. And then our transforms that we want to do are equal to transform. So then we'll comment this load training data. And then we're going to make the test data set as well, equal to data sets dot cipher 10. It'll be the same root slash data. The train is false on this one, but download is also true. And then same transforms. And move that S. Comment this. And now we're going to also instantiate our data loaders. So it's going to be equal to data loader, train data set, and the batch size equal to batch size. Shuffle will be equal to true. And then test loader will be very similar, except it's going to be on the test data set. Same batch size though. But the shuffle is going to be false on this one. Like that. And you can see I already have them downloaded. So now we're going to instantiate our model again. It's going to be equal to the same thing. And then we're going to make the number of classes 10, because that's cipher 10 data set, and I'm bringing this to the GPU for me. If you don't have a GPU, then don't worry about that. Our criterion is going to be cross entropy loss, like that, and then our optimizer is going to be equal to optim.atom, takes in the model dot parameters, and then learning rate is going to be equal to learning rate, like that. Alright, we're good. So now we're going to instantiate the training loop, so training loop, like that. Alright, so for epoch in range, number of epochs, we're going to train our model. So like that, model.train, we're putting it in training mode there. Batch numbers equal to 0. And then for images, labels in train loader, we're going to 0 the gradients on our optimizer, like that. And then we're going to feed the data into our model. Images. Oh, it appears I've run out of time. We're gonna keep going anyway, and we're gonna bring this to our device, so the GPU for me, and then loss is going to be equal to the criterion between the outputs, labels, and then we need to bring these onto the GPU as well, since we're computing the loss. And then we're doing loss.backward, optimizer.step, that. And then if our batch number modulus 200 is equal to 0, we're gonna print it. We're gonna print the loss, like that. And then we need to do the dot item, and we're gonna do to the 4 floating points, and then batch is equal to batch number, like that. Yeah, that's right. And then we're going to increase the batch number. And then after this, we're going to evaluate. So we're going to put it in eval mode so the weights don't get changed. And then we're going to set some values, so the correct number will be 0, and then the total will be equal to 0 at the start. And then with torch.noGrad, so we're not changing the gradients here. For images, labels, and test loader, the outputs are going to be what we feed into our model. So it'll be very similar to the original training loop, just this time we're not changing the values. Be equal to torch.max outputs.data, and then dimension 1. Total is going to be plus equal labels.size 0, and then the correct is going to be equal plus equal to the predicted, where the predicted is equal to labels, and then we need to move these to our GPU as well because we haven't yet. And then we're going to sum it up and get that item. And then the accuracy is equal to the correct divided by the total, like that. And then we're going to print it. So it's the epoch, and then epoch plus 1, because it starts at 0, and then number of out of the number of epochs, and then loss. Yeah, let's do that. That'll be equal to loss.item, same kind of thing we did before, and we're going to do the same there. Accuracy, accuracy, and that'll be also down to that, like that. And then afterwards we're gonna do torch.save, so we're saving the model weights like that, and then we're gonna call it simple CNN model path, and we start training. Just like that. You can see everything's working, clock's going down. These are models built correctly. Oh. One moment. So the issue here is that this needs to be images. Now we'll continue. And there we have it. So you can see we finished training. Our model is right here. So real quick, we're actually going to evaluate our model just to make sure everything is working correctly. So how are we going to do that? We're going to start out by saying data iter, and we're going to go through all of our test images like that. And we're gonna go through and get all of the images and labels. Like that. And then so we're gonna do all of our classes. So I googled these beforehand to know what the different numbers represented. So it goes plane, car, bird, cat, deer, dog, frog, horse, ship, and truck, like that. Now we are going to get a list of all the test images that we want to use, and because we're displaying these using matplotlib, we're gonna have to transpose the image so that the number of channels is, I think, at the end. Yeah, it has to be at the end. So we're gonna make a list. So we're gonna start with the first image, and then we're going to transpose it. So we're bringing the second element to where the 0th element is, and then vice versa. And we're going to do this for all of our images, like this. And we're done. So we'll just run that. So now we're gonna actually plot images and predictions, like that. So I'm gonna do the figure axis equal to plt.subplots. Fig size is 10, 6, like that. Now we're going to plot images. That's our first step. So plt.subplot. This is the first one, like that. Oh, this needs to be 1. That was a mistake. And we're gonna set the title, so t.soup title. Go plt.show. Oh. Here you can see cat, ship, plane is the ground truth. Don't mind the warnings, they're just because all these images are normalized. Now we're gonna reload our model to test it. It's the same model, but we're gonna make a new copy of it. I'm gonna copy the path. Then we're gonna get the outputs equal to model images I think yeah, let me check something. It should be fine. And then underscore and the predicted equal to torch.max. So that we're gonna need the maximum argument of the outputs for each, and then that's on dimension 1, and then we're printing predicted like that, and then we're joining an F string J and range 4. So you can see, delete that. We put dog, ship, plane. Close. Only mistake was with the mistaking the dog for the cat. So that proves that our model's working. So if you liked this video, make sure to like and subscribe. I'm actually going to be making a new YouTube channel called SaberSauce0 that's going to be mainly production videos. So if you're looking for something a little bit less technical, that's a little maybe higher quality editing rather than projects, you could feel free to check that channel out. There will be a new video on there soon. So anyway, that's it. I'll see you next time.